Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss another very important method for the estimation of the water hardness, and the name of the method is the soap titration method, which was developed by the Clark. That's why the method is also known as the Clark method, right? As you know, the basic definition of water hardness is what? The soap consuming capacity of any water sample is called its hardness. So in this soap titration method, actually what we do, we actually determine the volume of the soap solution which will be required by the sample water for the precipitation, right? As you know, in the water sample, generally your calcium and magnesium ions are there, which generally causes the hardness. However, apart from these two ions, other ions may also be present, but this particular method is actually typically for this magnesium and the calcium hardness, right? Because they are present in abundance in the water sample. That's why we generally take the calcium and the magnesium ions, right? And you know, when you add the soap solution to the water sample and these magnesium and calcium ion reacts with the soap to form actually the insoluble scum. As long as these ions are present in the water sample, your water will not produce any kind of the lather. Once you have precipitated these calcium and the magnesium ions as this insoluble scum, and these ions completely removed from the water, only after that your water sample will produce the lather, and that amount of the soap which is consumed by the water sample is equivalent to the hardness present in the water sample. This you have to remember. So what I have done here, I have taken the example of the sodium stearate, right? However, you can take the other examples also. Sodium palmitate, sodium laurate are also there. So this is C17H35COONA. This is your sodium stearate, which is nothing but soap. And when you add this soap to the water sample, basically this is your water sample. I have written Mg2 positive here, but basically it is your water sample. So what I can do, I can write here water sample, right? And in this water sample, your magnesium and calcium are present. So you are adding this soap to this water sample, and these calcium and magnesium are reacting with the soap, and they are producing the insoluble scum or insoluble white precipitate, which is nothing but your calcium or the magnesium stearate. You can replace this M with the calcium or the magnesium, right? But I have I have written this equation as the generalization of M2 for M2 positive ions, right? But you can replace this M with the calcium or magnesium, right? And in turns, equivalent amount of the sodium ion would be released into the water sample, and you know these sodium ions will not cause any kind of the hardness, right? So what is the method actually? For this you need to know the lather factor. Lather factor is nothing but it is the method of minimizing the error. See, whatever the method we will adopt in that case, right? In all the cases, whether you are calculating your temporary hardness, whether you are calculating your permanent hardness, anything you are doing, right? So you need to consider this lather factor, and this lather factor is actually is used to minimize the error actually, right? So if you subtract this value of lather factor from the original volume of the soap solution, which will be consumed by the water sample, this will actually minimize the error. So what is lather factor? Lather factor is nothing but it is the volume of the soap solution required to form the lather with distilled water. So here in that case I have written the distilled water, but generally you should remember this particular point, that distilled water should be of zero hardness, right? Zero hardness. So basically generally we say that it is of zero hardness, but it is not possible. When you are when your water is distilled water, right, as I have written over there, and it is considered that since the water is distilled, there should be no there should be no metal ions present in the water sample, but it does not happen actually, right? So this distilled water also consume little of the soap solution and form this insoluble scum, right, before forming the lather, right? So this is actually the lather factor which we need to subtract from any tighter value you need. This is very important, right? So I hope this is clear. Now moving to the next slide. So my first method, see what I am doing. First I am doing the standardization of the soap solution. If you have seen my lecture of estimation of water hardness by EDTA method, then there also I have explained the method of the standardization. If you haven't seen that particular video, I am giving you the link in the description box. You can go there and watch that particular video also, and that method is also very important for the BTech first year students, right? And I'm also, see, the link is also flashing at the right top corner of your screen, right? You can click on the link also, right, if you want to watch that particular lecture. So first, in the first step, I am doing the standardization of the soap solution against the standard hard water, you know, so that we will have the information about the soap solution also. Okay, so for standardization of the soap solution, what we do here, see, we take the standard hard water, and this standard hard water is generally prepared by dissolving a paste of calcium carbonate in the double distilled water. In the double distilled water means it is not having any kind of the hardness, right? And the method is given in the theory and practice of engineering chemistry by Vermani and Nerula. You can go there how we can prepare the standard hard water. This is given there, right? So here what we do, will fix the hardness of the standard hard water as 1 gram per liter, right? 1 gram per liter, please remember. So I will dissolve 1 gram of the calcium carbonate in the 1 liter, right? This is very important, you need to understand, right? And see, this is your burette, and in the, you see here, glass-stoppered bottle is there. I am not using the flask here because I need to shake this reaction mixture vigorously each and every time, right? That's why I need to take the glass-stoppered bottle, right? So here I have taken the soap solution in that. Whatever the soap solution I am having, I will fill that burette with the soap solution, and in the glass-stoppered bottle I will take the standard hard water, and I will take the 50 ml of the standard hard water. Please remember, I will take the 50 ml of the standard hard water, which is something very important which you should note. And then I will start the titration. So here in the standard way it is written that you add 0.2 ml. So if it is not clear, if it is not very clear to you, so what I can do, I can remove it, 0.2 ml, right? So it is the standard procedure that when you are standardizing your soap solution, you need to add this soap solution in the quantity of the 0.2 ml from the burette to the conical flask. However, you can go in the other way also. You can proceed drop wise also. Generally, we do the titration very slowly, and we need to add the titrant in the very low volume, say drop wise you can adapt, but here I am using this method 0.2 ml. So what I will do here, I will add 0.2 ml of the soap solution to it, right? And then, you know, this soap solution is now coming here, that is sodium stearate, and this is also having the hardness causing ions, which is calcium and the magnesium. And then I will put stopper on this particular glass stoppered bottle, and I will shake vigorously this mixture. I will shake vigorously, and will notice any formation of the lather is happening or not in the this particular flask. And then if it is not forming the lather, then again in the next step, again I will add 0.2 ml of this, and again I will shake vigorously, right, to the vigorously this reaction mixture, right? And again I will observe whether the lather formation is happening or not. Once I have observed that, little lather is forming here, then I will add drop wise soap solution from the burette to the reaction mixture, and I will shake the reaction mixture well, and I will stop my titration at that point when my lather actually persists at least for the 2 minutes. That means when your lather persists for the 2 minutes, that means the reaction has been completed now, right? And that volume of the soap solution will note, and we will do the calculation. So we will record that volume as the V1 ml. So here I will record that soap solution as V1 ml. And for this standardization, I'll see, I have taken what? 50 ml of standard hard water, SHW, right? See, if I go back, you see here what I have written here, I'll take 50 ml of the standard hard water, right? So I'm taking the 50 ml of the standard hard water, and this 50 ml of the standard hard water, now I have straightforward jumped to the this step number 4, because it is very important to calculate the lather factor before doing further calculation. So that's why I am doing this method, right? I'm going to calculate this lather factor. So what for this lather factor, what I will do, again I will take the soap solution in the burette, and here I will take the water of the zero hardness, that means the distilled water. Water of the zero hardness means distilled water. And again I will repeat the same procedure which I have explained for the standardization of the soap solution, right? So what I will do, I will add again, see, drop wise. So for I'll add soap solution drop wise. However, you can go like 0.2 ml addition of soap solution to this glass stopper bottle. So I'll add this what drop wise, or the 0.2 ml you can go, but I prefer drop wise. So you add a drop of the soap solution and stopper the bottle, shake the reaction mixture well, and notice any formation of the lather happening or not, right? And you continue this process in the same way as I have explained for the standardization of the soap solution. And whatever the amount of the whatever the volume of the soap will be consumed in that case of the lather factor, you will note this value as the V4 ml. Please remember, you will note this value as the V4 ml. And I already told you that this lather factor is important to minimize the error in the volume determination. So we need to subtract this value of the V4 from the standardization of the soap solution value, or the total hardness value, or the permanent hardness value. In every case we need to subtract this particular volume. I hope this is clear to you. Now I am moving back and I am going to the first slide. I have came back to this particular slide, a standardization of the soap solution. And if I go back, you see here for the standardization I have taken 50 ml of the standard hard water. That means whatever the V1 ml of the soap solution, this V1 ml of the soap solution consumed by this water sample to precipitate all the hardness causing substance and to give the lather, is actually equivalent to the 50 ml of this, right? So in the next slide what I can do, I can write this 50 ml of standard hard water is actually equivalent to the V1 minus V4, right? This V1 is actually the soap solution consumed by the standard hard water, and this V4 is actually the lather factor, right? And this actually of ml of the soap solution. Why soap solution? Because this V1 ml, this V1 ml is what? It is your soap solution. Here you can see this V1 ml is the soap solution, and if I go further, this V4 ml is again, it is what? The soap solution, right? Please remember this particular point. The method is very important. So I can write like that. Okay. So what actually it implies, that V1 minus V4 ml of soap solution, ml of soap solution, okay, is actually equivalent to the 50 milligram of CaCO3 equivalent. Why this 50 milligram of the CaCO3 solution? Because made this water sample as 1 gram per liter hardness it is containing. It simply means 1000 ml is having 1 gram of CaCO3. Your 1000 ml is actually equivalent to 1000 milligram of CaCO3. So definitely your V1 minus V4, which is actually used by this 50 ml of the standard hard water, this actually equivalent to the 50 milligram, because 1000 ml contains 1 milligram. So 1 ml will contain the 1 milligram. So 50 ml will contain the 50 milligram. This you need to understand. This is very, very important. And now you know we always do the calculation in the same way as you have learnt in your junior classes. We'll use the unitary method. For 1 ml of soap solution, this is actually what? 50 divided by V1 minus V4 milligram of CaCO3 equivalent. Okay, 50 milligram of CaCO3 equivalent. So this is the first method actually, right? And now moving next, the next method is what? Determination of the total hardness. See, in that case I have see this value, whatever this value will come, this will have the numeric value. Whatever this value will come, we will incorporate this value in the calculation of the volume of the soap solution for total hardness as well as the permanent hardness. And I already told you it is very, very important in the water chemistry. We use the calcium carbonate equivalent. It is very, very important. In my earlier lecture I have explained why it is necessary to convert all the hardness causing substances into the calcium carbonate equivalents. So we need to incorporate this particular factor in each and every calculation which we will make during this method. Okay. So now my next method is the determination of the total hardness. Now again same thing I'll do. I'll take the soap solution here, which I have already standardized, and I know I know the data about this soap solution. And now fill that same soap solution in the burette, and in the glass-stoppered bottle I'll take the 50 ml of the sample water. Now I am not using any your standard hard water. I am using the sample water, and this sample water may come from pond, it may come from lake, it may come from the sewer, it may come from the tap, from anywhere you can take this water sample. And I'll apply the same method. Same method means, so I'll add drop wise, or you can say the 0.2 ml of the soap solution, but I'll prefer in lab actually. See, this is the standard procedure, but in lab I'll prefer the drop wise addition of soap solution to the water sample. I'll add the drop wise, or in that case, in the present case I am taking the 0.2 ml. So if you add the 0.2 ml to the soap solution, and again I'll stopper the bottle and shake the reaction mixture well, and I'll notice the formation of the lather, whether it is happening or not, and I'll keep doing this addition of this 0.2 ml until I observe any formation of the lather in that in the glass-stoppered bottle. Once I'll observe the formation of the lather, then I'll slowly add drop wise add this soap solution to this same bottle and shake the reaction mixture well, and I'll end this procedure of determination of the soap solution volume when my lather, which is formed into the bottle, right, in the bottle, will persist at least for the 2 minutes. So it is very, very important. Your lather must persist at least for the 2 minutes, right? When your lather persists for the 2 minutes, stop the reaction and note this volume of the soap solution which is consumed by the sample water, and this value this volume of the soap solution I'll note as V2 ml. I'll note this value as V2 ml. Now I'll do the same calculation. So calculations for the total hardness is what? Again you see I have taken the 50 ml of this, so I am writing here 50 ml of sample water. So here I am writing sample water. Okay, this sample water is equivalent to what? This V2 ml. Okay, and I already told you from this V2 ml I always need to subtract the value of the lather factor, which is very, very important, and this much ml of soap solution. This much ml of soap solution. Again I'll apply the unitary method, right? And before applying the unitary method, what I'll do, I'll convert this volume of the soap solution into the calcium carbonate equivalent. So I am writing here in terms of CaCO3 equivalent, in terms of CaCO3 equivalent. So for this, what I will do, this is equal to V2 minus V4, okay, and this value will be multiplied by 50 divided by V1 minus V4. And this is again very important. Now you must understand that from where this value is coming, right? Because this is the normal soap volume of the soap solution, and it is mandatory to convert all the hardness causing substances, right, into the calcium carbonate equivalent. So I need to incorporate this value which I get from the standardization of the soap solution in the previous step. If I go back, right, you can see here 50 divided by V1 minus V4 milligram of the calcium carbonate equivalent. So once I have incorporated this 50 by V1 minus V4 here, so this is naturally in terms of the calcium carbonate equivalent, right? And you know, when you determine the total hardness, you always determine the total hardness in milligram per liter or in your ppm. ppm and milligram per liter are same. ppm equals to milligram per liter. That means you need to do the calculation for the 1 liter. So for 1 liter, I am writing for 1 liter, or you can write 1000 ml of sample water. So I am writing SW, not sample. Sample is fine. Sample water. This is equal to what? V2 minus V4 is already there. There is no problem in that. And this 50 divided by V1 minus V4 came from the standardization of the soap solution, and we need to multiply this value is with 1000 ml, and you have calculated for what? 50 ml. So divided by 50 you should add here, okay. 50 gets cancelled, okay, and you will have the expression like that: V2 minus V4, okay, divided by V1 minus V4. It is very important to put these value of volume in the bracket, okay, multiplied by 1000. So this is automatically in milligram per liter or ppm. So if you know the value of the V2, that is this value, if you know the value of the lather factor, and if you know the value of the V1, that means standardization of the soft solution, then you can easily determine the total hardness of the water sample. So this is your total hardness formula. Please remember, it is very important, right? Now moving further, this is my next method. This is my next step, not method, next step, determination of the permanent hardness, right? So how I can determine the permanent hardness? For this, I will take the 500 ml beaker, and into this 500 ml beaker I will take the 250 ml of the sample water, right, which I have used earlier for the estimation of the total hardness, and I'll boil this water or this 250 ml of water, and I'll reduce this 250 ml of water into the 50 ml, so that all the temporary hardness will remove from this particular water sample. If you know the basics of the water hardness, you know temporary hardness is removed by the boiling of the water in an open container. Please remember, this beaker should be open, right? All the carbonates and the bicarbonates decompose by the heating, and the carbon dioxide will evolve, and in the sample water you will only having the permanent hardness then, okay. So this is 250 ml. I have reduced it by boiling to 50 ml, and I'll filter the precipitate if any, right, and collect all the washings and precipitate that washings again, collect the washing again, and this 50 ml, I'll adjust this volume again to 250 ml, because this 50 ml will not be enough for me to do the titration. So I'll add 200 ml, further 200 ml water of zero hardness, so that I can make the volume 250 ml. However, hardness will not change in that case. Still it will contain the total hardness, it will contain the permanent hardness only. I am only increasing the volume by adding the water of the zero hardness, so that my volume is enough to do the experiment, right? So this now 250 ml water, I'll 50 ml from this 250 ml which I have made here, I'll take the 50 ml into the glass stopper bottle and fill the soap solution into the burette, and again I will proceed in the same way. That means the addition of 0.2 ml of soap solution. This is the standard procedure, but I'll prefer the drop wise. And again I'll apply the same procedure which I have explained for the step 1 and the step 2, right, until my precipitate, my lather, not precipitate, my lather persist in the glass stoppered bottle at least for the 2 minutes. I will stop the reaction and I'll note this volume of the soap as V3 ml. So I'll note this as V3 ml. Okay, now the calculation, how I'll do the calculation for this permanent hardness in the same way, right? So if you know, see, if you follow this, if I go back, sorry, right here you get this value, V2 minus V4, V1 minus V4, okay, and this is determination of permanent hardness. What I have done here, I have taken 50 ml of boiled water, 50 ml of boiled water I have taken, okay, and this 50 ml of boiled water, what it has taken here, if I go back, this 50 ml of the boiled water has consumed V3 ml of the soap solution. Please remember, so this 50 ml is actually equivalent to the V3 ml, and I need to subtract the value of the lather factor in each and every case to minimize the error. This much ml of soap solution, this much ml of soap solution, right? And now I need to convert this into the calcium carbonate equivalent. So V3 minus V4, right? And again I'll do the same thing which I have done for in the second step, 50 divided by V1 minus V4. This actually is coming from the, see, you know from where it is coming. It is coming from the standardization of the soap solution. Please remember, once I do this, this is basically is what, mg of CaCO3, mg of CaCO3 equivalent, right? And now you know we always do the calculation for 1 liter. So for 1 liter or 1000 ml, right? See what I will do here, I am doing in the different manner. So for 1 ml, same thing, it is what, V3 minus V4 divided by V1 minus V4. I'll put like that, okay, multiplied by 50 is already there. I'm doing for 50 ml, so again this 50 is here, okay. This is mg of CaCO3, and I'll do this for 1000 ml or for 1 liter. So this will give you what, 50 gets cancelled. So this is what, V3 minus V4 divided by V1 minus V4, okay, multiplied by 1000 milligram of CaCO3. So this will be your what, total hardness. So the only difference in the two expression is what, here you are using the V3 minus V4 and we divided by V1 minus V4 multiplied by the 1000. In the earlier case, you are having V2 minus V4, nothing else. Check here, V2 minus V4, right? This is something very, very important. Okay, now you can go for the temporary hardness also, right? So for temporary hardness, for this is for permanent hardness I have done. Okay, temporary hardness. Okay guys, so however, see, once you know the value of the total hardness, you can simply subtract the value of the permanent hardness from the total hardness to get the temporary hardness. But in the Clark method, sometimes it may happen that in your examination, or say in your internal examination, or during your assignment, your examiner may ask the how to derive the expression for the temporary hardness. So it is very important to do this particular thing also. See, total hardness, okay, that total hardness equal to what? Temporary hardness plus permanent hardness. And if you want to calculate temporary hardness expression for temporary hardness, this is what? Total hardness minus permanent hardness. And for total hardness, you are having this expression. Please remember, for total hardness, you are having the expression V2 minus V4 over V1 minus V4 multiplied by the 1000. So I will write that expression here, V2 minus V4 divided by V1 minus V4 multiplied by 1000. Okay, and then minus expression for the permanent hardness, and for permanent hardness you are having this particular expression, V3 minus V4 over V1 minus V4 multiplied by 1000. So here I will write V3 minus V4 over V1 minus V4, both in the bracket, important, multiplied by 1000. Of course, this will be in the ppm. If I solve this particular expression, so what I will get here, you see this 1000 and V1 minus V4 is common. Okay, so what I will do here, 1000 over V1 minus V4 I took common here. Then I need to incorporate another bracket. Now I left with the V2 minus V4 minus V3 minus V4 and this much of ppm. So your temporary hardness would be like that, 1000 divided by V1 minus V4. Okay, now this is what? V2 minus V4 minus V3 plus V4. Sign change when we open the bracket, this much of ppm. Okay, then your V4 gets cancelled and your final expression is like that. This what you left with? V2 minus V3. So you will write here V2 minus V3. In the denominator you are having V1 minus V4, V1 minus V4. Okay, and this is multiplied by 1000, this much of ppm. Okay, so you are having three different kinds of the expressions, and I can summarize all those expression here. First expression for your total hardness. Now recall and write along with me in your notes. Total hardness, for the expression for the total hardness was what? Total hardness was equals to V2 minus V4 divided by V1 minus V4 bracket into 1000. Okay, and for permanent hardness, your expression was V3 minus V4 over V1 minus V4 multiplied by 1000. Don't forget to put the unit ppm, and temporary hardness. You have just written that expression here. V2 minus V3 over V1 minus V4 multiplied by 1000 ppm. So this is the method, and this method is quite straightforward and simple, and by using this particular method you can calculate the total hardness, temporary hardness and the permanent hardness, right, of the water sample. In the next lecture I will explain a numerical based on this particular method, and I will not use this particular derivation there. I will start in a fresh way. I hope you understood the lecture well, right? Go through this lecture, this is important, right? And I'll meet you in the next class. If you are new here, please subscribe the Tetrahedron chemistry classes and do share with your friends also, okay? And if you like the video, don't forget to like it, okay? Thank you very much.